maybe we can use it later as well. Did the bell start? I mean, did the class start? Yeah. Okay, so go to your project. We're going to work on page 13. And it's the page that has these little cartoon diagrams, like there's a monkey, a windmill. You got it? Get there? And you got it. Good. Good. 13. Okay, so on this page, we're going to be making some energy diagrams, or these are really models of the amount of energy in different systems. Okay? And we're just going to do these together one at a time. And then we'll move on from there. You should be able to do these kinds of diagrams on your own, both for the last couple pages of the project and for the exam. Okay. So our first diagram is going to show a monkey dropping from a tree. So this is very much like what we've been doing already with different things falling, right? The other two diagrams are going to be a little different. They're going to be different kinds of energy that we haven't really talked about yet. So the first thing, I find it easiest to do these on the computer if you can draw a square. So if you go to these drawing tools at the top and draw a rectangle and just put it anywhere you want right now. And once you've drawn that square, then right click and then hit properties. And because we're going to be making a bunch of different squares of different colors. Okay, so we need to be able to change the color of the square. So this one I'm going to make here, this allows me to change the edge of it, so I'm going to make it blue. And then if I want to fill it in, I have to go over here. And then I say OK, and I have a blue square. So one of the things we're going to do is start by looking at the energy changes as the monkey falls from the branch, right? So when it's just hanging from the branch, it hasn't let go yet. What kind of energy does it have? When it's just hanging there. Sorry? Yeah, when it's just waiting to fall, when the energy is stored, then it's potential energy, isn't it? And it's all potential, huh? 100% potential. So when we show the amount of energy in this box, how much of the box should we fill in? Yeah, we should fill in all of it. So this is what I'm going to do. First of all, I'm going to go to this square, and I need to make a key that explains the different kinds of energy I'm showing in the diagram. So the first thing I'm going to do is write key over here, or legend if you like that better. And then I'm going to show that my blue box is potential energy. Because we got to explain everything as we go, right? Especially if we're just using different colored boxes, we got to say what they are. So we're going to make a key, little by little, we'll add more to it as we build it up. Okay, next, I know that the monkey only has potential energy when it's just hanging from the branch. So I'm going to fill in this entire box with blue, correct? Now here's the easiest way to do that. You could make a new box and change its properties, but the easiest way is if you click on that box, you activate it, and then you copy and paste it. And I found the easiest way to copy paste in this is to use the keyboard shortcut. So if you hold Control and hit C, that's for copy. Control V will paste it, and you'll get another blue box. It shows up in the middle. And then you can drag it over here, and we can change its size and shape to match what we want to be. And in this case, it's easy because it's 100% potential energy right now, huh? Perfect. How are you doing? You make a box, okay? You just keep it there. Oh, okay. Right click on it. Properties. And then fill color. And then choose color. Okay. Now, you know how to drag this to where you want it to be, right? Hang on. Okay. Put it over it. Right on that edge in the middle. There you go. You got it. Drag it down to where you want it. And then change the fill to match that one. Okay. So now we're going to go to the next box down. The monkey has fallen halfway. Let's see, I'm going to put that up there. The monkey's fallen halfway down. So if it's halfway to the ground, what kind of energy does it have now? Now it is actually falling, isn't it? It is actually moving. And remember, potential energy is stored because of its position. And when it's up in the air, it has the potential, it has the possibility of falling. So it has that potential energy. But now it's moving too, isn't it? And what do we call that energy of movement? Started with K, right? Kinetic energy. So now if it's halfway to the ground, what percent of the energy is kinetic exactly? And what's the other 50% of the energy? If it's half kinetic, but it isn't all the way to the ground yet, what's the other 50%? Yeah. So we're going to make another box for potential energy. And since I already copied it, I think all I have to do is hit Control V. Yeah. And I got that the potential energy box. This time it's only halfway potential. And then I need another box to make for kinetic energy. So for this one, I have to change its color. I right click, I hit properties. I'm going to make this one red. Make it whatever you want it to be. Remember, on the left, you can change the outline. On the right, you can change the fill. What is this one? And I'm going to use this first one because I have to add it to the key, right? Got to remember to add things to the key as we go. This was kinetic energy. And so now this energy diagram with the monkey halfway to the ground basically shows it 50-50. Okay, and then we have the very moment that the monkey hits the ground. And I think there's one thing that's kind of weird about the diagram, the way that they show the ground, um, and they've drawn the ground through the middle of the energy diagram box. And we want to just ignore that, okay? That doesn't have anything to do with what you should do in that box. We're going to put our colored boxes right on top of it anyway. So at the very moment it hits the ground, what does it have? Kinetic, potential, both? Yeah, so at this point, it's hitting the ground, and at the very second it's reached the ground, it can't fall any further. There's no potential left, is there? So at that very moment, it's going to be 100% kinetic. So make another kinetic box and fill that in. For me, it would be all red, right? You got it figured out, I think. Okay, now the last thing you need to do, I'm not going to make this box, so some things you got to do on your own, but it should be all kinetic, right? So the last thing you have to do is justify your reasoning. Explain why you made it all potential at the top, half potential and half kinetic at the bottom, and all kinetic at the bottom. So explain that. But I have one other question for you first. Look at the total size of the boxes. The overall size of those boxes. So if we look at the size of the one with the monkey hanging and the size with it in the air, the size with it on the ground, how do the size of those boxes compare? The overall size. Is any one bigger or smaller than the others? Or are they the same? That's exactly right. They're the same because what's the law? Yeah, you're on the right track. What's the name of the law? The law of, in fact, it might even be at the top of the page, is it? Basically, it is. Energy is conserved, right? Or it's the law of conservation of energy. What does it mean to conserve? Well, it's never lost, it's never gained, but we can change it, huh? We can't destroy it. We can't create energy. We can't destroy energy, but we can convert it from one kind to another. And is that exactly what this diagram is showing? The total amount stays the same, doesn't it? But it gets converted from potential to kinetic along the way as the monkey drops to the ground. All right? So I wanted to point that out, and then go ahead and write out your explanation down here where it says justify your reasoning. Make sure you filled in this box for yourself too. So explain why we did it all potential at the top, half and half in the air, and then all kinetic at the bottom. So you're going to do that yourself where you're justifying the reasoning about the monkey, right? It's kind of a small space for it, isn't it? You can overlap beyond those lines if you need to. Yeah, and then it's halfway, right? That's why this is two. It stays the same mass, huh? So that's good. Right? This one, you're gonna have to use square root to get your answer. Okay, let's move on to the windmill. You need to finish your explanation later, you can do that. But let's do the diagram parts together. So to start with, we have a windmill, and it's being, well, the windmill's gathering the power of the wind, huh? So what kind of energy does the wind have? What is wind? Isn't wind just moving air? Like, and there was plenty of it this morning, huh? I could hear the lake splashing around and the wind in the trees. So the wind is moving air. But wait a minute, if it's moving, what kind of energy would that be? It would be kinetic energy, right? So for the first one, we're starting with the energy in the wind, and it's going to be all kinetic. So our first box shows the beginning amount of energy from the moving air was 100% kinetic energy. Okay, so now we're going to start converting the energy of the moving air into electricity. And the first step is we have to turn those windmill vanes, we call them. And inside the windmill, we have these gears that are part of the turbine. And they are spinning around too, huh? So what kind of energy is that? If they're spinning, if they're turning, isn't that also movement? So that's still kinetic energy, huh? But don't you think that as they're turning, they're making some noise? So some of that energy of the moving wind is lost, it becomes sound. And don't you think there's also some friction between those gears? And friction results in heat, right? So we also lose some energy to heat. So what I'm going to do is I'm going to start off by making another box for kinetic, And I'm just going to estimate that about 3/4 of it remains as kinetic. So I'm going to take this down here. Sometimes if it's hard to move your boxes around and stuff, it helps to zoom in. So I'm not going to fill in that entire box with kinetic because we had some energy lost because of sound and heat. We have losses of energy. So what two types of energy did I mention we were losing? Heat or thermal energy. Thermal energy is the same as heat. And what was the other one? Sound, yeah. So we need to make two new colors, one for sound and one for heat. Okay, so I've chosen my two colors for sound and heat. And now I'm going to take that section of the top section next to the gears and divide it in half and make one half of that sound and one half of that heat. Remember Control C to copy, Control V to paste. Okay, now, this is something we didn't do yesterday, so you might want to do this with me. So basically, I want to remind you that the sound and heat went out into the air. So what we're going to do is we're going to grab a pencil and we're going to make an arrow, and I'm going to do it kind of a wavy line, like it's lost. So both of these are lost from the windmill. Not very good arrows, but oh well. As long as we can tell what they are, it's okay. And then we're going to say that this is energy lost to the air. The sound and heat are lost to the air. Did they get destroyed? No, they were just lost from the system, right? They still exist in the universe, but they're not in the windmill anymore. So can we use any of that sound or heat to make the energy for the light bulb to glow? It's lost. We can't use it, can we? We only have this kinetic energy is available to make energy from, which means that down at the bottom, the most energy we could have is only going to be the same amount as this. Right? And so we end up having a blank section at the bottom diagram because we lost that energy. But wait a second, is that kinetic energy in that light bulb? Is it moving? It's not moving. What kind of energy is it giving off? That there's some heat that's wasted, and we're going to come to that, but what kind of energy are we trying to get? That light bulb is showing that it's making light, right? Yeah. So I need to make another new color. I'm going to change this one to be light. I think I'll use, what have I not used? I've used red, blue, green, use orange. I'm going to use purple. And of course I have to add it to the key over here too, huh? But wait a minute. Do you think that all of the kinetic energy in the gears got converted into light? Or did we also have some more losses along the way? Yeah. For instance, at least the old type of light bulbs, they heat up, don't they? And we lose that energy. Also, there's some energy lost in the wiring of the electricity. So the first thing I'm going to do is I'm going to take this box and I'm going to make it smaller because we lost some more energy. Some of it was lost as heat. I've already made a box for heat. So I'm just going to copy that box. But then some of it is lost in the wiring due to what they call resistance. So I'm going to make a final box of a different color to represent the loss of energy because of electrical resistance. We'll just call it electricity. So that's yet another kind of energy to add on our key, right? I'm just going to put electric energy down there. So I want to remind you the top half of this is left blank. We leave the top half blank because we've lost energy. This energy got lost. And so did this energy. So we should do the same thing we did with that. We're going to show this energy is lost. I'm showing it as like waves of energy coming out of the system. So the way we've drawn it is that only 50% of the energy from the wind ended up in the form of light. Not that the rest was destroyed, but it was just lost to the air. There is no such thing as 100% efficiency when it comes to our machines. So for example, on a car, the reason we buy gasoline is so we can move from one place to another, right? But doesn't the engine get really hot? And that takes energy to do that. That energy is coming from the gasoline, but it doesn't do us any good. It's lost energy, and it makes burning the gasoline less efficient. We lose some of the energy. We're actually paying to heat up our engine every time we start it up. The same thing would be true about other aspects. Oh, the sound of the engine. That takes energy to make that sound, and some of the energy in the gasoline is used to make that sound. So it's a loss of efficiency at every step of the way. So once you've finished these diagrams, once again, you're going to go down to the bottom and justify your reasoning. You're going to explain why we did what we did. There are some vocabulary words for you to use at the bottom of the page. Wouldn't use all of them on every diagram, I don't think. But also, in this case, we're going to include some ideas about sound and heat and electric energy. And we want to talk about energy losses also, right? How energy is lost to the air. So take a couple minutes and write up your justification. Explain what happened there as we go from the energy of the wind to the energy of the light bulb. The square root. Let me just check my answer key. Actually, in a way, this is too simple. Okay? So GH is just meters squared per second. But I have to go back and finish doing this. Okay, let's move on to the third one with a slingshot, right? So now, if we look at the slingshot, at the beginning, and if I take a rubber band, for example, when I first pick it up, how much energy is in here? Let's say this wasn't broken. How much energy is in there? When I pick it up, none. We're already done with the first one for the slingshot when it's relaxed. It has no energy in it yet, okay? There isn't any energy there. So we can move straight to the second one, where we've stretched it out. Now, when I stretch out a rubber band, I'm putting energy into it, huh? And this is also a type of potential energy. There's really two kinds, at least two kinds, maybe more, of potential energy. One is gravitational potential energy. It has the potential to fall because of gravity, right? This one's not about gravity, though. What is it stretching a rubber band? And then it comes back again. What did we call that kind of energy that's because it can change shape? Elastic energy. So this is, its full name is elastic potential energy, but we're just going to call it elastic energy. So have we, in the second diagram, have we put energy into it when we stretch it out? Yeah. And it's, at this point, it's all elastic energy, which we haven't used yet. So we need yet another box and another entry in our key. I think it would be best if you didn't use white. I had some students that wanted to make a white box, but when I look at it, I might not see it when I grade it, right? So maybe use something besides white. So the first box is blank because there's no energy in it yet. Then when we stretch it out, it's 100% elastic energy. Then when we let go, all that elastic energy is transferred into the stone, huh? And the stone goes flying through the air. So what kind of energy would that be? If it's moving, it must be kinetic energy. But hang on a second. Do you think that energy was 100% efficient? Or were there some energy losses along the way? Like when I stretched out that rubber band and let go, wasn't some friction causing a loss of heat energy? And then wouldn't it make a sound when it released? So once again, we have sound and heat being lost to the air. And then finish up by explaining why these things happen. Why was there no energy at the beginning? That should be part of your explanation too. Don't just ignore that first one. Explain why there's no energy there. Then explain what's going on in the second diagram. Explain what's going on in the third diagram. Then we're going to move on to finish this on your own by doing the math problems on the last couple pages. The first few math problems, they fill in a bunch of stuff for you, and you just have to do it. But you got to pay attention so you know how to do it the next time. And then by the last problem, you're doing it all on your own. Okay? All right, so I'm going to end this meeting now, and later on I'll post it to YouTube.